This video is covering angles and different ways to measure the angles. We'll also look at formulas for arc length and area of a sector or a part of a circle. And then finally we're going to look at what are called linear speed and angular speed of objects traveling in circular motion. So those are our objectives for this section. So first we just need to develop some terminology for angles and how we talk about them. So what I'm going to sketch here will be a sketch that describes the definitions of an angle, an initial side, a terminal side, positive angle, negative angle, and the standard position. So I'm going to sketch an angle in what's called standard position, and if we imagine a set of axes, XY axis, putting the vertex of the angle at the origin and putting what's called the initial side on the positive x-axis. That's what we call standard position. For an angle. Then, if we picture an angle whose terminal side is over here, so rotated in a counterclockwise direction from the initial side. Why doesn't that underline? This would be considered a negative angle. Alright, I think my pen's working now. So again, the initial side, if it's on the positive x-axis, that's called an angle in standard position. And now, if we rotate in a counterclockwise direction for what's called the terminal side, then that's called a negative angle. Sorry, positive angle in a counterclockwise direction. And if we rotate the other way, so have our initial side there, but rotate in a clockwise direction, that's called a negative angle. So we've got an angle, initial side, terminal side, a positive angle, a negative angle, and standard position, all defined. Then an example, the first example here, we're just going to draw a few angles in standard position. So 135 degrees in standard position, we would want the initial side on the positive x-axis. What you want to keep in mind is that there are 360 degrees in one rotation, or 180 degrees in half a rotation, 90 degrees in a quarter, and then 45 halfway through each quadrant, which would be what, 1/8 of a rotation. So for 135 degrees we could think, well, 135, that's 90 plus 45. So a quarter of a rotation and then 1/8 after that. And we want to rotate in the counterclockwise direction. So this would be 135 degrees in standard position. Right? So an angle with the same distance or the same rotation between the initial and terminal sides would still be 135 degrees, but this is how we would draw it in standard position. Negative 120 we could think of that as what, negative 90 and then negative 30. So we would want to rotate, if we have the initial side here, rotate in the clockwise direction a quarter of a turn, a quarter of a rotation, and then a third of the next quadrant. So something like maybe here, roughly. And then 540 degrees, we'll sketch over here. We've got more than one rotation, right? I'm going to get out my calculator. And I want to figure out 540 minus 360. And you could probably do that in your head, but if you can't, just grab a calculator. So we've got a one complete rotation and then 180 degrees more than that. So we're thinking 540 is 360. 360 degrees plus 180 degrees. So we're going to do one complete rotation if this is my initial side. One complete rotation, and then 180 degrees more than that. So the terminal side would end up on the negative x-axis. Something like that. Alright, and then what we're going to talk about is another angle measure called a radian. And the definition of a radian is that if you have a circle that has radius r, so let's draw that circle. So r can be arbitrary radius. If we take that length, r, so that distance out from the edge, that's called r, the radius. And then we picture taking that same length and wrapping it around the edge of the circle. So without a piece of string or something, it's hard to do that. But if this distance is also r, then this angle here is 1 radian. So wherever we put that radius around the edge, the distance or the angle that's formed by connecting each of those sides of that arc length to the center, that interior angle there would be called 1 radian. Right? So that's the definition of a radian. If we want to know how many radians are in one circle, you might already know, but what we can think of is that the arc length for one revolution is exactly the circumference of the circle. And you probably, maybe hopefully remember that the circumference of a circle is 2 pi times the radius. Right. Or 2 pi r. So if we have a length of 2 pi r For a circle of radius r, the number of radians in that circle then must just be 2 pi. So what we've got is a connection between degrees and radians. So we'd have 360 degrees has to be the same as 2 pi radians, which you can abbreviate RAD if you'd like. And that is easier if we reduce on both sides, so that 180 degrees is the same as pi radians. And this is usually the connection we use to convert back and forth between the two angle measures. So these two conversion factors are just built from that connection that we just made between degrees and radians. If we want, if we have degrees and we want radians, then we would choose the right conversion factor to cancel. So here we've got 51 degrees. We want the degrees to cancel, and we want to be left with radians. So we can put our labels in, and we know that pi radians is 180 degrees. So the degrees are going to cancel. So we have 51 over 180 pi radians. We can reduce that. 51 and 180 are both divisible by 3. 51 divided by 3 is 17. And 180 divided by 3 is 60. So the best form of that answer would be 17 pi over 60 radians. And then if we want to go the other way, we have negative 5 pi over 6 radians, and we want that as degrees. Then we would put radians in the denominator and degrees in the numerator, so that the radians will cancel. Pi radians in 180 degrees. So now we're left with negative 5 pi times 180 over 6 pi degrees. We can reduce the pi over pi, and then 180 over 6 is 30, so it looks like negative 150 degrees. Alright, then what we want to do is develop a formula for the length of an arc that's subtending a central angle of theta radians. Let's see what we can do here. So the picture we're thinking of is we've got a circle of radius r. We have an angle in here of theta radians, and we want to know what's the arc length right here. That's called the arc length for a sector. And we can show where this formula is coming from before we use it. Let's do a proof over here on the side. The entire circumference would be 2 pi r, because we'd have 2 pi r for the whole circle. And what we can use for the proof is that the ratio of the interior angle to the entire number of radians in one revolution should be the same as the arc length compared to the circumference. Right, so the ratio of the part of the angle, or the angle that we have to the entire number of radians in one revolution should be the same as the ratio of the edge that we have to the whole edge. So that means that theta divided by 2 pi is the same as s divided by 2 pi r. And what we're looking to do here is solve for s. So this would imply that s is 2 pi r times theta over 2 pi. And the 2 pi's cancel. And so we've got this formula that s is r times theta. You want to be careful to realize that this formula is only good if the angle is measured in radians. If the angle is measured in degrees, then you need a different formula, or you need to convert the degrees to radians, one way or the other. So you want to memorize this formula, but when you're memorizing it, make sure that you remember that theta has to be in radians. So example 3 here, if we're looking for the length of the arc of a circle of radius 6 meters, subtended by a central angle of pi over 3 radians, everything's given to us in the nicest form. So that's our theta value. This is our r value. And we're looking for s. So we'd say, well, we'll just use that formula. S is r theta. So we'd have 6 meters times pi over 3 radians. Looks like that'll be 2 pi. And the label on the arc length would be the same as the label on the radius. So if the radius is measured in meters, the arc length would be in meters. Then the next example here, example 4, is again looking for arc length. So we're looking for s, but we've got an angle of 120 degrees. So we need radians. And the radius is 5 meters, so we've got our r value given. So the first step would be convert 120 degrees to radians. So we would take 120, we want degrees to cancel, so we'll put 180 in the denominator and pi in the numerator. So 120 over 180, those are both divisible by 60, so 2 pi over 3. Alright, so that's our theta value. And then the second step, we can say s is r times theta. So we'd have r times theta, it would be 5 times 2 pi over 3. So 10 pi over 3 meters. So what we can do is write down another formula for arc length if we want to. If, let's say instead of theta, let's call it alpha is given in degrees, then to convert it to radians, we would multiply by pi over 180. And that would be then an angle in radians. So we'd have r theta then, and we could just use this. So we can say the angle in degrees times pi times the radius divided by 180 would work if angle is in degrees. The main thing is just to remember that s equals r theta will only work if we're given the angle in radians. Alright, one more example here with arc length. Here we've got a central angle that's not given, if we know the circle is radius 10 and we know the arc length is 12, we've got to figure out what's that angle going to be. So we've got circle radius 10 and arc length of 12. And we want to know what's this angle. And we want the angle both in degrees and radians. So we can use our connection S equals R theta as long as theta is in radians. And we can say, well, the S is given, that's 12. The R is given, that's 10. So it looks like theta would be 6 over 5 radians. That's one part. And then we also need theta in degrees. So we'd multiply by degrees in the numerator, radians in the denominator, so that the radians will cancel. So we've got 6 times 180 over 5. over 5, that's going to be 36. So 36 times 6. (216 over pi degrees). All right. So obviously that S equals R theta is the thing we're using to get going on any of these problems. We need to have 2 of those pieces of information to be able to find the third. All right, so there was our second part of that one. Then, looking at a formula for the area of these circular sectors. Again, let's draw our picture. Again, this formula is only going to be good for angles given in radians. So if we've got that given radius and we've got that given angle, we want to find the area that's shaded. So the area for just that region would be 1/2 r squared theta. And just like we did in the other one, I want to go through a proof of that so it doesn't seem like it's coming out of nowhere. And we'll do the same thing. We would set up 2 equal ratios. So the angle out of the total number of radians in a revolution should be the same as the sector area out of the entire area. Which means theta over 2 pi should be the same as what we're calling A in our formula, and the circle area is pi r squared. So if we solve for A, we have pi r squared theta over 2 pi. The pi's cancel, and we've got the formula that's given. So this is another formula that's worth memorizing. But if you don't memorize it, hopefully just going through this proof you can kind of come up with it yourself, as long as you remember the formula for the area of a circle and that you can set up these ratios that should be equal. And just like the other one, I want to emphasize again that theta has to be in radians. If theta is in degrees, then you can convert it to radians first and then use this formula. So, like in example 6 here, we are given that the central angle is 135 degrees, so we need radians. So we would convert 135 degrees to radians by multiplying by pi over 180. (135 over 180) 0.75, so 3/4 pi radians, or 3 pi over 4 if you prefer to say it that way. So that's our theta in radians. So we can say the area is what we're looking for, 1/2 r squared theta, and the diameter is 10 meters, which means the radius is 5. Because the diameter goes all the way across. So we'd have 1/2 times 5 squared times 3 pi over 4. So that's going to give us, what, 75 pi over 8? And since the radius was in meters, the area would be in square meters. One more sector area example. Here, the radius is given and the area is given, but we want to find the angle, so we don't know theta. And so once again, we'll use this formula that A equals 1/2 r squared theta, if theta is in radians. And we can fill in the values that we know. So we know A, and we know the radius. We don't know theta. So we'll solve for theta. Let's see. If we multiply both sides by 2, and we'll then also divide by 24 squared. It's going to give us 1. So it looks like the angle is 1 radian. And to convert to degrees, we'd multiply by 180 over pi. So we're going to get exactly 180 over pi degrees. So we've got the angle in radians and also in degrees. So you'll notice that some of these numbers we're coming up with look very strange, but it's best to leave them exact like this rather than to type onto your calculator 180 over pi and get a decimal approximation. And the same will be true in MyMathLab. On the quizzes and tests and things, you'll make sure that you just leave these answers exact unless they ask you for an approximation. Then the last thing we need to talk about in this section are these ideas of linear speed and angular speed. And what you want to think about is an object moving on a circle. You might want to track the actual distance the object is moving per each unit of time. So like, how many inches per second is this object moving? That would be what's called the linear speed. But if you're focused on the angle instead, and how quickly that angle is changing, maybe like, this many degrees per second or this many radians per second, then that's what's called the angular speed. What you want to focus on is the units in each one, or the labels in each one. If you're talking about linear speed, you're actually tracking the distance that's moved per time. But if you're looking at angular speed, you want radians per unit time, or sometimes you would want degrees per unit of time. So Usually it's in radians, but if the problem is specifying that they want degrees, that's fine too, but an angle measure per unit of time. So I would recommend not focusing as much on these formulas as on what labels you want when you're done and what labels you're given. So for example, if we look at this example 8, it's saying we've got a car wheel with diameter 30 inches. Which means the radius is 15. Makes 10.8 revolutions per second. And we want the angular speed, and we also want the linear speed, and they're specifying miles per hour for the linear speed. Let's do angular speed first. And let's say we want radians per second, since the time is given in seconds. What we're given is 10.8 revolutions per second. So let's start with that. We're happy that we see seconds in the denominator, but we need to convert revolutions to radians. And there's nothing special about this particular circle. We know that every circle, one revolution is 2 pi radians, right? Because that's how many radians are in a revolution. So that's a connection that we can use for any circle, not just this one. So we'll multiply by 2 pi radians per revolution. Just using dimensional analysis, we can get the right units to cancel out. And now we've got 10.8 times 2 pi radians per second. Let's do 10.8 times 2 here. So 21.6 pi. So there's our angular speed. And now if we want the linear speed, we can use the angular speed that we know, 21.6 pi. We've got radians per second. And we want to get to miles per hour. So we've got a ways to go because we don't have miles or hours here. But we can multiply by the right factors. It'll be easy to convert seconds to hours, so let's not worry about that yet. If we have radians, another connection we can always use is that one radian is equal to the radius length. Right? That's how the radian is defined, is that if you've rotated one radian, the distance traveled is one radius. So we can do, the radius for this is 15 inches per 1 radian. Right. Let's write those as inches, IN instead. So we can always get the radians to cancel by putting the radius length in the numerator and then the radians in the denominator. And then we just need to get from inches to miles. So we can do inches to feet, feet in the numerator, inches in the denominator. We've got 12 inches in 1 foot. And And then we can do feet to miles. Feet we want canceled, miles left. 5,280 feet in 1 mile. So now we've got miles like we want, but we want seconds to hours. So either you could get there directly, 60 seconds in 1 minute, or you can do 3,600 seconds in 1 hour. If we go to minutes, then we'll need one more 60 minutes in each hour. So, inches will cancel, feet will cancel, miles will stay, seconds will go, and minutes will go, and hours will stay. So we'll have miles per hour like we want, right? And then you'd grab a calculator, multiply all of the numerator factors together. I don't have a space to put it. So 21.6 times 15 times 3,600 divided by, and the denominator factors looks like 12 and 5,280. And I'm going to get that as a fraction. 405 over 22. Pi, we still had in there too, miles per hour. So we could get an estimate of that. 405 over 22 pi. So approximately 57.83 miles per hour. Right, but our focus was on what are the units we've got at the start, and how are we going to use dimensional analysis, just canceling things out to get to the units we have at the end. So these two connections that I have in these rectangles are helpful to get between revolutions and radians, or revolutions and then all the way to a length, a distance traveled. Alright, I'm going to go teach a class. I'm going to pause this and then I'll come back and do example 9 in a minute. On example 9 here, we're looking at another example of linear speed and angular speed. First thing, make sure that you change, there's a typo here, and the information changes from the start of the problem to the end. So make sure that you switch that both of these pulleys have radius 3 and 9 inches. So the smaller one should be 3 inches, the larger one would be 9 at one point in the problem. It says 9 and then it says 8. So make sure that large one is 9 inches in both parts. And the information that's given tells us that the 3-inch pulley, the smaller one, is rotating at 5 revolutions per minute. And we want to use that to figure out how many revolutions per minute the 9-inch pulley is making. And then what we're going to use is that the linear speeds have to be the same because they're moving with the same belt, right? So for the smaller pulley, I'm going to use dimensional analysis for this. So we know that the angular speed is 3 revolutions per minute. And we want to figure out the linear speed. So we would want to know like inches per minute. Right? So we want to work our way canceling out units from revolutions to get to inches. Right? So 3 pi revolutions per minute, we know there's always 2 pi radians per revolution, And because the radius here is 3 inches, we know 1 radian is 3 inches, so 3 inches per radian. So then we can cancel the radians, cancel the revolutions, and we'll have inches per minute. And that has to be the linear speed for the belt, because that's the linear speed for the small pulley. So we've got, looks like 9 times 2, so 18 pi inches per minute. So this would be the linear speed for the small pulley and the belt and the large pulley. Because they would all have the same linear speed. So now what we want is for the larger pulley, what's the angular speed? What is the revolutions per minute? So we know we've got 18 pi inches per minute, and we want to get to revolutions per minute. So we want to work our way from inches to revolutions. There we know the radius is 9 inches, so we have 1 radian is 9 inches, and then we want to have 2 pi radians per revolution. So 1 revolution is 2 pi radians. Then the inches would cancel, radians will cancel, we'll have revolutions per minute just like we want. So it looks like we've got 18 pi in the numerator and 18 pi in the denominator, so we end up with just 1 revolution per minute for the larger pulley. There are certainly other ways to get through this problem, but I would highly recommend using dimensional analysis to work through these linear and angular speed problems. Just think about what are the units that I've got and what are the units that I want. And then remember that what's consistent from one problem to another is that we always have 2 pi radians in 1 revolution and 1 radian in whatever the radius length is. Those two pieces should be able to get you between linear speed and angular speed, kind of back and forth. There's an error here in what I just did in this problem, so let's go back and fix it. I had a mistake about the number of revolutions per minute. I had written 3 revolutions per minute, and it should be 5. Otherwise, I think everything's okay. So let's erase that 3 and make it 5. So if we have 5 revolutions per minute times 2 pi radians per revolution times 3 inches per radian, then instead of having 18 pi, we'll have 30 pi. So let's fix that. So 30 pi inches per minute. Then we can use that calculation in the next part here for the larger pulley. Change that 18 to a 30. So 30 pi inches per minute times 1 radian per 9 inches for the larger pulley times 1 revolution per 2 pi radians for any revolution. And that's going to give us then, let's see, 30 divided by 2, and the pi's will cancel. So we'll have 15 divided by 9, it looks like. 15 ninths, so what's that, 1 6 ninths, or we can reduce that. If we divide everything by 3, we'll have 5 thirds, 1 2 thirds. So that should be the answer in that problem, 5 thirds revolution per minute for the larger pulley instead of 1. The number of revolutions went up from what we had before for the smaller pulley, and it makes sense that they would go up for the larger pulley as well.